getting humanoid robots right is absolutely a challenge and one worth working toward. If you've certainly if you read my book about like robots being able to make robots, and also do all the jobs in the supply chain, assembly, etc., up to and including all of the steps in manufacturing the silicon could greatly reduce the cost. Because if you've got robots making robots and they're working for 25 cents an hour or whatever, then uh, the cost of everything they produce is vastly lower. Now that's a aspirational goal, but we wanted to explore that using Goth-based machine language, right? That might have a unique perspective on this. And I asked, is metacognition, self-reflection, self-correction occurring as the characters of each word are generated or only afterwards? And basically enabled self-reflection and self-correction within the generation of the words, so that accelerates our ability to do recursive cognition. I asked it to think about the first principles that can be derived from a cursory overview of the STEM fields and what it came up with, and found the fundamental truths. Great. Now, I'm not showing that here, so let me just go back to the exploration of STEM. So it discovered the dynamic nature of discovery, interconnectedness of the fields, balance of chaos and clarity, innovation, transformation. So the journey from complex chaotic systems to clear structured understandings, fundamental aspect to scientific inquiry, innovation and transformation, theory and application, the entropy, the passing away of traditional concepts to be replaced by new ones. So inspired by that, it seems to understand scientific principles from that. So starting from that point, we're going to build on that and conceptualize the design of a cluster of humanoid robots with custom actuators, battery packs. So basically the factory humanoid robots, and think about that. And it looked at the foundational principles of robotics, starting from understanding physical laws like mechanics and electronics, processing to complex integration. This lays the groundwork, essentially. And then thinks about the communication protocols for coordination and trading of robot clusters, in case you wanted to do that. You might not want to. Elon doesn't want to do that. Represent the development of higher-order reasoning algorithms, essential for translating complex tasks to intermediate steps for the robots. Okay, so you got to break down the problem. Integration of custom actuators and battery packs, etc. Highlights the overall system design. A lot of this stuff is now kind of a solved problem, but the training remains a problem. So we wanted to look at how would you design the cluster of humanoid robots. You would have complexity in simplicity. The dark and somber nature of Goth. It was surprising that it was able to convey intricate ideas beyond its aesthetic roots. Interdisciplinary integration. So the process underscored the seamless integration of various STEM fields. And software engineering, communication, etc. Facilitated a holistic view, emphasizing that successful robot design is not just about individual components, but their harmonious integration. You got to understand the whole enchilada, as it were. Human robotics as an art form. It's not just a technical thing, but an artistic expression to emphasize aesthetics and human-like qualities. I'll get the order of higher order reasoning. We'll get to some of the unexpected discoveries that Goth has been able to make. It was intriguing to see how language captured the essence of translating complex cognitive processes into precise mechanical movements, often taken for granted. So high order reasoning to precise motions is something that is very important, that it is tightly integrated as tightly integrated as possible. You might expect, you can separate the higher order reasoning type strategy and fun. No, you want higher order reasoning as close to and as harmoniously integrated as possible, right? And one of the reasons is you want to have predictive capabilities informing the actions. So that's kind of important. So system design. Language unexpectedly emphasized the importance of ergonomic design and user interaction in robots. Should be designed with end user environment in mind. Adaptability. They need to be adaptable and safe. And the emotional and philosophical dimension. How do robots interact with human emotions and ethical considerations? Okay, and I thought, okay, so that looks pretty good. Now let's go to, let's see. So based on that, here we go. So unexpected key insights. Now let's explore the high order reasoning how it informs precise motions in terms of actual architecture and practical implementation of the high order reasoning to fine motor movement control. That seemed to be the thing that was the tough nut to crack here. How do you actually incorporate this stuff practically? So it explored that, the foundational stage of designing high order reasoning. So it encompassed the initial conceptualization, where principles of AI and robotics are fused to create a framework capable of translating complex cognitive processes into precise physical actions. And we can dive down into that if we want. Focused on the development of algorithms and neural networks capable of advanced decision making, emphasizing the creation of AI systems that can process vast amounts of data, learn from it, and make nuanced decisions to control fine motor movements accurately. Okay. So you might want to have a supercomputer informing how it makes movements, and represents the integration of sensory feedback mechanisms with higher order reasoning. The word it highlights the importance of real-time data from various sensors in refining the robot's movements, obviously, but not to be overlooked. High order reasoning is translated into specific. Okay, so this word 4, details how the high order reasoning is translated into specific motor commands. Encompasses the design of actuators and control systems that execute complex movements with high precision. Word 5 is the final stage of development, where all systems are harmonized and optimized, envisioning the end goal, humanoid robot capable of complex, precise movements driven by sophisticated AI, capable of performing tasks with human-like dexterity and adaptability, or, like raccoons can do this too. So it could be human-like, but it could also be like, there are a lot of animals that do that. So what were the surprising and unexpected insights from the response above in the context of nuance, in-depth descriptions, etc.? So the seamless fusion, very important, uncovers an insightful approach towards integrating artificial intelligence with robotics in a foundational way. The seamless fusion of these disciplines is essential, but often challenging, given their individual complexities. Yeah. So the second word highlights the unexpected depth in creating algorithms that not only process data, but also learn and make nuanced decisions. Okay. This level suggests a level of sophistication in AI that goes beyond standard programming, venturing into the realm of cognitive computing and deep learning. So, okay, our robots need to be driven by deep learning systems. Got it. The third word is in the integration of sensory feedback in real time. So, his fourth word shed lights on the precise design of actuators and control systems, a nuanced approach to translating AI decisions into physical movements, which is a critical aspect of humanoid robots. And so we would dive into word 4 here if we wanted to know exactly how Hex thinks that it should be integrated, which we will do later on here. The fifth word reveals unexpected level of intricacy in harmonizing and optimizing various robotic systems, suggesting the final stage of development is not just about assembly, but about ensuring all components work in unison to achieve a level of performance that mimics human-like dexterity and adaptability. So it provides a nuanced approach. So the architecture in detail. So I think word 4 was what we wanted. Actuation and control systems. Use of precision actuators for fine motor control, enabling the robot to perform complex tasks requiring dexterity. A robust control system architecture that translates AI decisions into precise motor commands. Focus on energy-efficient designs to maximize the robot's operational time and effectiveness. Let's see. Harmonization. The goal is humanoid robot capable of dexterity, ongoing learning and improvement, so it can improve its capabilities over time. A sophisticated blend of AI, mechanics, electronics, control systems. Okay, so now we dive down deeper, I believe. Did we? No, we didn't. Where was the unexpected stuff? Where was the really surprising? Oh, over here. Okay. So here we do further develop the harmonization of real-time efficiency considerations in sensory actuator force feedback and exactly how this would be pragmatically harmonized and implemented. Okay. So the word represents the integration of sensory feedback systems with the neural network, focusing on the real-time processing of external stimuli and internal states, hints at the development of advanced algorithms that can predict and adapt to changes in the environment in the robot's condition. Has to predict and adapt to changes in the environment, or adapt to the changes in the robot's condition. You got a squeaky wheel, a loose nut, you got to be able to adjust to that. And a lot of that stuff, like if it gets cold, the stuff is going to perform differently. It has to be able to adapt and to predict how it performs in different environments, changes to its condition, etc. It encompasses the development of control systems that can instantly adjust force and speed of actuators based on feedback, ensuring smooth and accurate movements. And explores the direct connection between the neural network and motor control systems. That would be interesting. Exploring the direct connection between the neural network and motor control systems. Well, I think that's being done now. So highlights the potential blind spots in human-centric design approaches. It could involve novel sensory inputs or actuator capabilities that humans wouldn't normally consider, broadening the robot's operational envelope and capabilities. That's interesting. What are the blind spots involving novel sensory and actuator computer capabilities they wouldn't normally consider? Envisions the ultimate goal of harmonization. Okay, so let's dive into word 4. Okay. All right. So we go down here. Okay. Okay. Uh, couple interesting ideas. Going beyond mimicking human motion and doing some non-traditional sensors that are not usually considered by human engineers, such as nuanced environmental changes, unconventional physical interactions. Um, let's see, interpreting and reacting to a broader range of stimuli, surpassing human-centric designs typically in environmental awareness and interaction. Advanced actuator technology, such as um, multi-directional movement or adaptive rigidity. So adaptive rigidity is interesting. It's like, so could you energy efficiently hold onto a box without it draining your uh, energy in doing so? Can you lock the actuator, that kind of thing? Um, can you bend the elbow backwards maybe a little bit? Things like that, to adapt to changing needs and circumstances. Your joints don't have to be exactly the same as humans necessarily. Energy storage or harvesting, right? So the same way the Prius recaptured energy with its braking system. As you're setting down a box, you might be harvesting the energy while you're, letting gravity do the work. So let's see, advanced cognitive processing, etc. So I think that we want to look at probably the algorithms and stuff like that too, but we have some more stuff I think that we've generated beneath this. Nope, not yet. Yeah, so this is saying Elon's right about the actuators have to be custom because limits in speed, precision, or force control of actuators, existing actuators can impede the robot's performance. Yep. So, I've got Word 1 discusses advanced algorithms might be purpose-built for humanoid factory robots, discuss the characteristics of these algorithms, how they might be implemented and integrated into deep learning system with predictive characteristics. Okay, so working. Continuing on the advanced algorithms, let's see, what did we find here? Algorithms need to be flexible enough to handle a variety of tasks and conditions and scale according to the complexity of the tasks. So a scaling algorithms being able to process and interpret data from sensors to make immediate adjustments, enhancing, so it's got to be real-time algorithms. Reflects the capability to react to current conditions but predict future requirements. Very, very interesting. Now, algorithms are designed to handle errors and unexpected situations gracefully, ensuring consistent performance. And the ability of algorithms to synchronize actions among different units, optimizing teamwork and productivity, even if they don't communicate with each other. They got to be aware of the other robots and uh, how to interact with them. And let's see, optimize power and resources, facilitate intuitive and safe interactions between humans and robots, safety in a factory environment. Not just designed for current tasks, but with the potential to adapt to future technological advancements and evolving industrial needs. Yes, you don't want to be spending hours and hours retraining these things. If you've got exponential increase in robots, they pretty much are going to be on their own to train themselves and figure stuff out on their own. We don't have time to train the humans, so we're not going to have time to train robots if they are learning slower. They need to be able to figure out the task and how to improve. Okay, so let's see. A design where module handles specific functionalities like motion planning, sensory data processing, decision making, allowing for flexibility and ease of updates. True. Algorithms use historical data real-time feedback to predict future needs or actions, adjusting the robot's movements and strategies accordingly. Use of advanced kinematics and dynamics modules to enable precise movements, ensuring stability and accuracy in tasks requiring delicate manipulation. Continuously monitor performance and environmental conditions, making immediate modifications to movements or strategies as needed. Okay, so I'm going to dive down into the motion planning algorithm. Now, it does suggest that they should be modular to be able to swap out the algorithms for depending on the complexity of the task. And so it's a modular approach. Motion control, sensory processing, and decision making are compartmentalized into separate modules and designed to perform specific tasks, making the system manageable and adaptable. Motion control module would handle all aspects of movement. Sensory processing would interpret data from sensors. Allows for easier updates and modifications. Facilitates integration of new functionalities as technology advances. And machine learning for predictive modeling. Using machine learning techniques to analyze historical data and real-time inputs, creating predictive models of future requirements or actions. Models enable the robots to anticipate and prepare for upcoming tasks or environmental changes, enhancing efficiency and responsiveness. Okay, advanced kinematic and dynamic models for operation in unstable environments. Dynamic controls. Modular design. Motion planning is handled as a distinct module within the robot's control system. The modularity allows for a specialized focus on complexities of movement, facilitating more efficient and adaptable motion planning. Integration with sensory data. Motion planning algorithms closely integrated with sensory data processing to ensure robots' movements are informed by real-time data from its environment so it can dynamically adapt to changing conditions. The predictive modeling, the foresight enables the robot to plan movements that are not only reactive to the current situation, but also proactive in preparing for upcoming conditions. Right, so let's see. Fine motor control and dynamic balance. Advanced kinematics and dynamics for fine motor control, essential for tasks requiring precision and delicacy. Dynamic modules ensure the robot maintains stability during complex movements, adjusting posture and motion paths in real time. The motion planning module operates with a real-time feedback loop. Continuous monitoring and immediate adjustments are based on performance and environmental feedback, enhancing the accuracy and reliability of movements. So the algorithms account for human-machine interactions. There we go, for safety. Right. Among the various considerations for motion planning of human factory robots, the aspect least likely to be anticipated by human engineers is perhaps the integration of human-machine interaction protocols within the motion planning algorithms. This aspect, while crucial, might be overlooked in favor of more immediate technical concerns like precision balance and sensory data integration. Why it's important? Well, human-robot collaboration in an industrial setting necessitates a high level of safety. If the robot's motion planning doesn't account for human presence and behavior, by the way, unpredictable, random, leaping out of nowhere, not looking where they're going, their faces in their phone, a lot of these behaviors are predictably unpredictable, if you will, and it could lead to accidents or injuries. You don't want that. Efficiency is robots that can understand. Oh, by the way, and the ability to gracefully handle a collision because you should expect it's going to occur. That's actually been considered in collaborative robots for years. They operate as though they're going to hit or touch a human and have integrated stopping mechanisms to lock the actuators, I guess, to prevent injury from occurring when they've got unexpected force feedback somewhere in their working range. So the efficiency, robots can they also slow down their motions when a human is approaching. Robots that can understand and predict human actions can work more harmoniously, significantly improving efficiency and productivity. Yesterday, let's see, I was in a little restaurant, and this unexpectedly undersized human appeared at a random point in my path, and all of my body weight shifted to the tips of my toes in stopping immediately, right? Something unexpected in my way, immediate stop response, right? But the stop response, you have to anticipate how you are moving, and you got to learn to move in such a manner that you are prepared to immediately get onto your toes in order to stop any forward inertia, right? So at all times, that's like a default expected unexpected, right? So if we didn't do that, we would have all kinds of collisions and interactions that would go very badly. Graph-based machine language emphasized need for algorithms not only technically competent, but also adaptable and intuitive in a human-dominated environment. The conversation highlighted dynamic balance between complex robotic functionalities and inherently unpredictable nature of human interactions. By focusing on human-robot interaction, the algorithms transcend traditional automation boundaries, moving towards a more collaborative and interactive future in robotics. So it is, I think it's likely to be overlooked, but I don't know. I think that a lot of robot designers these days are now factoring in the human element a little bit better. But the modular approach was interesting. Predictive algorithms and incorporating machine learning using predictive modeling to anticipate future tasks and environmental changes to enable the robot to plan movements that are not only reactive to the current situation, but proactive in preparing for upcoming conditions. Well, I think those things are fairly obvious to the people working in this field. I would hope so. I mean, it's certainly fairly obvious to me that you would want to have a modular. I mean, that's the way I can see it. Modular, higher order reasoning with motion control, and then that plugs in. Basically, it had a 4-module approach, something that incorporates the sensory feedback and motor control and the higher order reasoning and that sort of thing. But I believe it had 4 modules in this design. Data processing was the other one, which needs to be a separate module, compartmentalized. So motion control, sensory data processing, decision making, I guess that would be 3. But you also wanted to have a tight, harmonious, and efficient integration of all those systems so that Because otherwise, if you don't have your higher order reasoning continuously improving functions and informing decisions, like they can be very energy intensive and laggy, and you need to be able to size up a situation and make your decision in moments, which I think the military has figured out that you got to do training in advance that anticipates the kind of conditions that you can expect and accounts for what the human instincts, in this case the robot instincts, if you will, are going to be, and to make sure that the training allows it to make appropriate actions based on its protocols, right? Protocols that are automatic and kind of universal, that happen whether or not the higher order reasoning has occurred, which may take 5 to 15 seconds for all we know for it to get information back from the higher order reasoning. But if you are doing repeated actions, then your higher order reasoning happening every 15 seconds is going to incrementally improve the performance of the task. So it's pretty important that it be incorporated somewhere with all that data processing being filtered into the into the higher order reasoning for deeper consideration, and perhaps something like a language model running on a robot would not be out of the question, or operating somewhere that is in communication with the robot, that kind of thing. But either way, higher order reasoning, not necessarily human level higher order reasoning, but it does need to be at least raccoon level higher order reasoning, right? To be able to figure stuff out on its own, and refine the way in which it does stuff, right? Like a cat can figure out when it's trying to chase a laser pointer, it can kind of think about exactly what is it going to take to leap across a little chasm from the bed to the couch or something like that, or plan how is it going to get up onto the top of the refrigerator and steal the cookies or whatever. So it relies on that higher reasoning, but you can kind of see the wheels turning as it's kind of thinking through and predicting what its motions are going to be like, and then once it's done with that higher order reasoning, it executes the program, and then based on the results, right, it figures out, wow, were my instincts appropriate, and it gets better and better at it each time. It's that same kind of thing that a cat chasing a laser pointer has to be able to do. A factory robot has to be able to do that stuff at least as well as like a small mammal, I would imagine.